Hello everyone, welcome back to this online class. I am Francis Okech and my YouTube channel is Professor Francis Okech. So today we are going to look at Calculus 2 and our main topic is on curve sketching. We need to know if you are given a curve or simply a graph, we need to be able to come up with the graph of a function y is equals to f of x. So what do you mean by curve sketching? You are given, I'm going to write, so we can write to sketch the graph, to sketch the graph of the function you're told y is equals to f of x. So what are we supposed to do? We need to find, so there are four things that we need to find. We do the following. In number one, we need to find what we call the turning points. In number two, we need to find the intercepts, that is x and y intercepts. Number three, you need to find what we call asymptotes. And in number four, once you have found those three things, then you use freehand to join the points. Maybe we talk of the turning points, x-intercepts, and even the asymptotes. So use freehand to sketch the graph. Use freehand to sketch the graph. So we need to know what is a turning point. We need to know what is an intercept. And we also need to know what is an asymptote. So let's start with the turning point. So the first item in curve sketching is turning points. Another name of turning points is critical points or the equilibrium points. So what do we mean by turning points? They are points where the derivative of the function, that is dy over dx, is equals to 0. So at that point, the gradient is equals to 0. So turning point can be classified into three categories. We can have a maximum point, a minimum point, and a point of inflection. So there are three types of turning points, three types of turning points. We have said the first one is maximum point. Another one is minimum point. And the last one is a point of inflection. So when you know the turning point, how do you classify the point? Normally, we use the second derivative test to classify the turning point. So to know whether the point is a maximum point, let's say let x naught, y naught be a turning point. On y is equals to f of x on this curve. So I want to use the second derivative test to be able to classify the turning points. So to know whether your point is a maximum point, you need to test whether the second derivative of y with respect to x at the point x naught, y naught, check whether the result is less than 0. Let me write less than, not equal to. I'll wrap this. So I'll wrap this one. We expect the result here to be less than 0 at that point. If you want to know whether your point is minimum, is you check the second derivative of y with respect to x, check if the value is greater than 0, of course at the point x naught, y naught. If the value is greater than 0, then it means that point is a minimum point. And if you want to know whether your point or your critical point is a point of inflection, then again using the second derivative test, d squared y dx squared at the point x naught, y naught. If the result is equals to 0, then you know the point you have is a point of inflection. That is second derivative test. But you could also use sign test. There are two ways of testing for a critical point, or simply the nature of that critical point. So the easiest is to use the second derivative test, or you will also use what we call the sign test. Sign test means at the maximum point, this is how the graph should behave. The slope should be rising, and then it levels, and then again it starts to fall. So that when it is rising, the gradient is positive. When it levels out, the gradient is 0. And when it is falling, the gradient is negative. What about a minimum point? This is what happens with the graph. The graph, it starts to fall, it falls, then levels, then again starts to rise. So that if you look at the sign of the gradient, when it is falling, it is negative. When it is leveling, when it has leveled out, it is 0. And when it is rising, the gradient is positive. And then on the point of inflection, a curve may rise, it levels, again continues to rise, or you may have a curve that was falling, it levels out, then it continues to fall. If you have a graph like that one, then that point is called a point of inflection. So for this one, when it is rising, the sign is positive, this is 0, negative, or the other one, when it is falling, it is negative, this is 0, then it is positive. So that is sign test. But it is easier to use the second derivative test to be able to classify the turning point. So having discussed turning points, let me see whether we can have an example, but I don't think, because we look at an example when we are now sketching a graph where we need to apply these concepts. So the next thing is intercept. Let me explain what I mean by intercept. So the second item that you need to find is intercepts. What do we mean by an intercept? Intercept, these are simply points where the curve points where your curve intersect or meets. We can write meets. You can also use intersects the axis. When you talk of two-dimensional x, y, check where your curve will meet the x-axis and check where your curve will meet the y-axis. Where it meets the x-axis, that point is called the x-intercept. Where it meets the y-axis, we call it the y-intercept. So there are two types of intercepts. The first one is x-intercept. And I said the x-intercept is the point where your curve will meet the x-axis. So at that point, you can say a point where the curve meets the x-axis. So at that point, what we know is that y is always equals to 0. When you're on the x-axis, the value of y must be 0. So you substitute, to find the x-intercept, you need to substitute y is equals to 0 into the equation that you're given, and then solve for x. So put y 0, then the next thing, solve for x. Another intercept is part B, what you're calling the y-intercept. So what do we know about the y-intercept? It is simply the point where, let me use a different color. It is the point where the curve meets the y-axis. And so along the y-axis, you know x is 0. So when you want to find the y-intercept, you put x is equals to 0 and then solve for the resulting equation. So in this case, x must always be equal to 0. So we need to solve for y. So that's all about the intercept. Maybe let me sketch so that you see. If I have this kind of a graph, xy, let's say my graph is like this, something like that. So where it meets the y-axis, this is what I'm calling y-intercept. Where it meets the x-axis, that is what I'm calling the x-intercept. So that is all about intercepts. Now, the next thing that you need to look for in when sketching a graph of any function, you need to look for what we call the asymptotes. So number 3, we are going to write asymptotes. Asymptotes. So what is an asymptote? An asymptote simply means an asymptote is a tangent to the curve y is equals to f of x at infinity. At infinity. Tangent lines, a line tangent to the curve at infinity. I can insert the word line. A line that is tangent to our curve at infinity. That means your curve and that line will only meet at infinity. That's what I mean. They can never intersect anywhere, but we assume that they will meet at infinity. Infinity here is a very, very big number. So we suppose that those two, the curve and the line will always meet at that very big point, the infinity. The infinity is written as this. So before we look at the types of asymptotes, let me illustrate an asymptote, an illustration before we look at the types. If we have a curve like this, let's say we have something like this, where here it is x, here it is y. And you have this line. That should be a straight line. Y is equals to x. So let's say that is the asymptote. Then your curve should be something like this. Should never intersect your line. So that in this case, let's say we also have another asymptote. Let's say this is an asymptote. This one is also an asymptote. If I were to draw a graph, it will be something like this one. Our curve can never intersect those two lines. Another one could be something like this. You see, you expect them to meet at infinity. So those are examples of asymptotes. So we have three types of asymptotes. The first one is what we call vertical asymptotes. So what do we mean by vertical asymptote? It's simply a vertical line, a line parallel. It is a line that is parallel to the y-axis, the vertical line. And how do we get the equations of line parallel to the y-axis? That the general equation is that x is equals to a constant. That's the general equation of a vertical asymptote. All lines parallel to the x-axis to the y-axis, that means x is equals to a constant. Then how do we get it? Let's say if you are given that f of x is equals to p of x over q of x. If you're given this rational function, then to find the vertical asymptote, you simply need to equate the denominator to 0 and solve for x. So to find vertical asymptote, comma, equate denominator to 0 and solve for x. That means that the points where q of x is equals to 0. So when you solve it, you get this equation will give you the values of x, and so those are the vertical asymptotes. So solve for x. Another one is number 2. Call it number 2. Number 1 was vertical. Number 2 is horizontal asymptote. When you talk of horizontal asymptote, they are simply horizontal lines. And so this means they are lines that are parallel, line that is parallel to the x-axis. What is the general equation of such kind of a line? That y must always be equal to a constant. The general equation of those lines parallel to the x-axis is that y is equals to a constant. So when you're given a function f of x is equals to p of x over q of x, how do you find the horizontal asymptote? So again, you can write that given f of x is equals to p of x over q of x. Of course, I ought to have said here that p of x not equal to 0. That's very important. P of x not equal to 0. Even here. So to find the horizontal asymptote, which you are going to call y, is simply the limit as x approaches infinity of f of x. And that will give you a constant if the limit exists. If the limit does not exist, then there is no horizontal asymptote. So this is the formula that you're going to be using to find the horizontal asymptotes. And what you need to take note of here, we can write a note that if the limit does not exist, then there is no horizontal asymptote. That is very important. When we say the limit does not exist, it means you get the limit and you have tried all the techniques of evaluating limit and your result is infinity, either positive infinity or negative infinity. If that is the case, then we say that the limit does not exist, yes, and so there's no horizontal asymptote. Another one is slant asymptote. So we write number 3, slant asymptote. What do you mean by slant asymptote? It is a line that is neither parallel to x-axis, neither is not parallel to x-axis, neither is it parallel to the y-axis. It is an oblique line. An oblique line. So that is what we call slant asymptote. And how do we find it if you are given a function? So you can say given that f of x is equals to p of x over q of x. So to find the slant asymptote, you need to express this function in the form, let me write the form. You need to express this function in the form of mx plus c, then plus maybe another function, I can call it g of x over q of x. And how do you get this form? It is via long division. So if you look at the linear part, this one, the linear part, that is what we are going to say y. Y is equals to mx plus c. And so that will be our slant asymptote. So that the slant asymptote, you say it is the equation y is equals to mx plus c. So what I've used here is long division. And in long division, you must ensure that the polynomial in the numerator is of degree higher than that in the denominator. Then you can perform long division to simplify that function. And then the part that corresponds to the linear equation, that is what gives you the slant asymptote. So having discussed what we need when sketching a graph, I want us now to look at an example. And so we simply look at one example. Let me write here, example. Just one example to illustrate the concept on how to apply what we have discussed here in sketching the graph of y is equals to f of x. So in part A, let's say we are told to sketch the graph of the function. I'll write the function. Part A, you are given y is equals to x squared, everything over 4 minus x squared. We need to sketch the graph of that function. So what we do, we start by finding the intercepts followed by turning points, and then the asymptotes. So let's find intercepts. Number one, intercepts. So what is the x-intercept? What you do, you put y is equals to 0 and then solve the resulting equation. So that means 0 is equals to x squared over 4 minus x squared. If I cross multiply, remember 0 is the same as 0 over 1. If I cross multiply, I'm going to get x squared is equals to 1, not 1, because 0, x squared will be equal to 0. If I cross multiply, so let me delete the 1. I expect this to be 0. X squared is equals to 0. So when you check the square root on both sides, you get x is equals to 0. Remember, the point is x is 0 and y is also 0. So our point is 0, 0. So that is our x-intercept. What about the y-intercept? Y-intercept. And I told you that when to get the y-intercept, you simply need to put x is equals to 0 and solve the resulting equation. So let's substitute x is equals to 0 into the given function. We're going to get this. We're going to get y is equals to 0 squared over 4 minus 0 squared. That is simply equal to 0. So that our point in this case will be 0, 0. So the x-intercept is the same as the y-intercept. So just have a single intercept that is at the origin. The second item that we need to find is turning points. And we said a turning point is where dy over dx is equals to 0. So we need to find dy over dx. Dy over dx. That should be, use quotient rule. Quotient rule. The numerator is u. The value of this denominator is v. So that it is u prime v minus uv prime. Everything over v squared. So when you differentiate this one, u prime, that is 2x times v, that is 4 minus x squared, minus u x squared, v prime, differentiate 4 minus x squared, you get negative 2x. Denominator, that is 4 minus x squared, and this is squared. So in the numerator, if I open the bracket in the numerator, what will I get? I'm going to get 8x minus 2x cubed plus 2x cubed, everything over 4 minus x squared, and that is squared. So you see, 2x cubed will cancel with the other 2x cubed, so we get 8x over 4 minus x squared, and this was supposed to be squared. So equate that to 0. So equate it to 0 and solve for x. So therefore, 8x over 4 minus x squared, and this is again squared, is equals to 0. Remember it is 0 over 1. So this means 8x is equals to 0, which means x is equals to 0. So what is the value of y when x is 0? So therefore, when x is 0 and I substitute in the given function, you get y is also equals to 0. So our point, turning point, is just one point, and the coordinates are 0, 0. The origin is the turning point. So we need to know the nature of that turning point. Now we use the second derivative test. Use second derivative test. This second derivative, we need to classify this point either as maximum, minimum point, or a point of inflection using this second derivative. So let's find the second derivative of y with respect to x. So I'm going to write d squared y over dx squared. Remember, second derivative is derivative of the first derivative. So the answer we got in the first derivative, that was 8x over 4 minus x squared, and that is squared. Again, use another quotient rule. So in this case, our u will be 8x, and this denominator, which is 4 minus x squared and everything squared, that will be our v. So when you apply another quotient rule, we expect to find u prime v minus u v prime, everything over v squared. So let's work out this. U prime, that is 8, times v, which is 4, minus x squared, and this is squared, then minus u, which is 8x, v prime, that's the same as 2 times 4 minus x squared. I'm using direct chain rule, then times negative 2x. So this is v prime. The dot here means a multiplication over v squared. So that will give us 4 minus x squared. This is supposed to be squared. Now we need to know the value of this second derivative when x is 0. You don't even need to simplify. So at x is equals to 0, or simply at the point 0, 0, you see the right, this is a function of x, so you simply substituting x is equals to 0. What will be our second derivative? D squared y dx squared. If I put x 0, you see the all of this will, I'll have this, I'll have 8 into 4, because x is 0, so 4 minus 0, and this is supposed to be squared, minus 8x, x is 0, so that will be 0. The whole of that term will be 0, over 4 minus 0, and this is squared. What should this give us? 8 times 4 squared, 8 times 4 squared, everything over 4 squared, over 4 squared. So that will give us 8. Our answer is 8 there. And so, because the 4 squared will cancel with the other 4 squared, so that no, it was, the denominator was supposed to be squared, so just a correction here. It is supposed to be raised to 4, because here it was squared. When you square it again, it is raised to 4. So this is supposed to be raised to 4. A slight correction. So I expect another 4 squared in the denominator, because it was supposed to be the whole of that squared. So that's the same as 8 over 4 squared is 16, which is equals to 0.5. The correction is on the second derivative in the denominator. It was supposed to be v squared. When you square v, you get 4 minus x raised to 2 raised to 4. The whole of that raised to 4. So look at the value of the second derivative at x is equals to 0. We are getting a positive value. Positive, we say this is greater than 0. And we said when the second derivative at that point is greater than 0, then we talk of a minimum point. So what does it mean? That the turning point that we have found, let me take it, this turning point is a minimum point. That's the only turning point that we have on that graph, on that curve. So what else do we need to find? We need to find the asymptotes. The last tool is what we call asymptotes. So you can write number 3, asymptotes. So I told you asymptote is simply a tangent to the curve at infinity. There are 3 asymptotes. So part A, we start with the vertical. Vertical asymptote, those are lines parallel to the y-axis. And the equation means x is equals to a constant. How do we find it? Equate the denominator to 0 and solve for x. Look at our function. We are told that y is equals to x squared over 4 minus x squared. So the denominator is what you are going to equate to 0. That is 4 minus x squared is equals to 0. So I want to solve for x. This means x squared is equals to 4. So when you take the square root on both sides, you get x is equals to plus or minus root 4, that is the same as 2. So we have 2 vertical asymptotes, x is equals to -2 and x is equals to +2. So there are 2 of them. We also need to find the horizontal asymptotes. Horizontal, I told you those are lines that are parallel to the x-axis. And so the equation of such kind of a line is y is equals to a constant. Now we are given y is equals to x squared over 4 minus x squared. So to be able to find the horizontal asymptotes, which are calling y, you simply take limit as x approaches infinity of f of x, or f of x here is x squared over 4 minus x squared. So because this is limit at infinity, divide numerator and denominator by the highest power of x in the denominator. So the highest power of x in the denominator here is x squared. So we are going to divide numerator and denominator by x squared. So in the numerator, we'll have x squared over x squared, that should be 1. 4 over x squared is simply 4 over x squared. X squared over x squared, that again gives us 1. So when we try direct substitution, that where there is x, we put infinity. So I'll call this direct substitution. Let's see what we'll get. We'll have 1 over 4. Infinity, when you square it, you still get infinity. Then minus 1. A big number squared is still a big number. And when you divide by a very, very big number, the result should always be equal to 0. So we expect that 4 over infinity should be equal to 0. This should be equal to 0. So we have 1 over 0 minus 1, and so that is equals to 1. So therefore we are saying that our horizontal asymptote is y is equals to 1. The limit exists. So that is the value, the limiting value gives you the value of y. And lastly, we need the oblique or slant asymptote. Let me use the term slant. Slant and oblique are the same thing. And I told you, for you to be able to find this kind of an asymptote, you must be able to rewrite your given function in the form of mx plus c plus another rational function via the long division process. So let's see if we can be able to rewrite our function y is equals to 4, now y is equals to x squared over 4 minus x squared. So using long division, this is what you'll get. Let me use a different color. We are going to have here 4 minus x squared. Then inside we'll have x squared. I am rewriting the given function. So you check, you have negative x squared and you have x squared inside. What do you multiply by negative x squared to get x squared? The answer is negative 1. So negative 1 times 4 minus x squared, we get negative 4 plus x squared. So that when I subtract, I'm going to get 4. So therefore, it simply means that when you have x squared over 4 minus x squared is the same as writing, it goes there negative 1 times remainder 4 over 4 minus x squared. A point of correction on the horizontal asymptote, we said 1 over 0 minus 1. Instead of 1, it should be negative 1. So just let's add a negative here. And negative here, we expect this to be negative 1. Even here, we expect it to be negative 1. So this is negative 1. The other one is also negative 1. That's a point of correction. I ignored the negative. So look at our function now. This is what we are going to say, let this part be y. Ignore the ratio, the other part that is rational. So this is our y. So in short, we are saying that the slant asymptote is y is equals to negative 1. But you see, this is not an equation of a straight line. It's simply a constant. And so what does it mean? That in this case, in this example that we have been given, the slant asymptote is the same as the horizontal asymptote. So there's no slant asymptote because the value of the slant asymptote is a constant. It should be, for it to be a slant asymptote, it must depend on x. Or simply it should take the form of an equation of a straight line. Y is equals to mx plus c. But you see x here is 0. There's no x here. So y is equals to a constant. That means it is horizontal asymptote. So what you say here, there's no slant asymptote. I'm going to write it, no slant asymptote. No slant asymptote. So we have all the tools necessary to sketch the graph. And so the final step is now to come up with the graph. So I'll call it number 4 is now to sketch the graph. What you do, come up with a Cartesian plane, x-axis, y-axis, that's 2-dimensional. Plot all the points we have here. We are going to mark all the points, and also you mark the asymptotes, and then I'll show you how to draw the graph. So what you are going to do is, first of all, draw the x. So let's draw our 2-dimensional Cartesian plane. I'm going to use a different color. Let me use blue to draw the axis, or let me use green. So this is what we'll have. I am going to draw the x and y axis so that we have this. We have vertical. Let me draw a better line. should be a vertical. Remember, we are using freehand, but when drawing the axis, you could use a ruler. For me, it is freehand. So this should be a vertical line. Another one is horizontal. So this is X, and this other one is Y. So, and where they meet, that is the origin. That is the origin. The coordinate is 0, 0. Now, let's start with the first tool. Our first tool was, let me just check up here. Our first tool was intercept, and we got that the intercept is the origin. X-intercept is 0, 0. Y-intercept is also 0, 0. So we go on the graph and plot it. So the point 0, 0, or X is equals to 0, and also Y is equals to 0. That is the point intercept. That's our first tool. Our second tool is the turning point. And we also found that 0, 0 is the only turning point, and the classification is that it was a minimum point. So the same point, and we know it is minimum. So you see, when you talk of minimum point, it means the curve at that point should be concave up. When it is a maximum point, then the graph at that point should be a concave down. So this is minimum. Our other tool, the third one, is asymptote, and we had 3 asymptotes. Of course, the horizontal one, we got y is -1. The vertical, we got x is equals to plus or minus 2. But we said there's no slant asymptote because we found y is equals to -1, which is a constant, and that will be found as the horizontal asymptote. So let's start with the vertical asymptote. The line x is equals to -2. Usually, it's advisable that you use dotted lines. Use dotted lines when drawing the asymptotes. I hope that is clear. So I'm going to use dotted lines to mean this is the line x is -2. I also want the other line where x is +2. So again, dotted. These are straight lines. So this is +2. The other one was -2. Those are vertical asymptotes. Horizontal, we found y is equals to -1. Y is equals to -1 is at this point. Y is equals to -1. So we use dotted lines. Again here, dotted. You can use your ruler to draw the lines, but when drawing the graph, just use freehand. So this is the point where y is equals to -1. So those are the tools that we require to be able to come up with this kind of a graph. So your graph should now look like this. Now let me change the color. I now want to use color blue. So let me change to blue. So because this is a minimum point, we expect that our curve at that point should be concave up. So it should be something like this. And also at this other side, but can never meet the asymptotes. And there's also another curve this side, another curve this side, another one is this side. As long as they don't intersect the asymptotes. So that is the graph of the function y is equals to x squared over 4 minus x squared. Usually when you are sketching graphs, you see, when we ask you to sketch, we don't expect you to use any software, but for verification purpose, to verify whether the graph that you have sketched is correct one, use this software. software. And our software that we'll always use when sketching the graph is what we call the GeoGebra. GeoGebra. This one, you can find it online, just install it in your PC. So this will help you to verify whether the graph that you've drawn is the correct one. But if you follow all the techniques or simply all the tools that we require to draw the graph, then you will find that whatever you've drawn is simply the correct one as compared to what you'll find from the GeoGebra software. So that's all about curve sketching. When we meet next time, we look at a different topic under Calculus 2. Thank you all for watching. Don't forget to subscribe to my YouTube channel. That is Professor Francis Okech. Let's meet next week. Bye-bye.